Hi, this is Sarvesh. I'm starting the review for uh, presentation for chest structure diagnosis for deep neural network. Uh, so starting with the presentation. So why X-ray diagnosis using convolutional neural network? So X-ray is the most common tool used by radiologists. X-ray requires significant training for clinicians to read and interpret the X-ray image correctly. Accurate classification of X-ray image is a vital task. Incorrect classification may lead to a wrong result. A deep neural network have performed extremely well for image classification, hence could very well be used for X-ray diagnosis. Advancement of big data techniques like deep learning is enabling the analysis of X-ray in a more real-time and automated manner. And availability of large dataset like NIH dataset or GSXpert dataset, GSRT dataset is now making uh, possible for learning X-ray images implementation using the convolutional neural network. And these datasets are helping to create a model which is almost 80% accurate. Going to the next slide. So datasets. So I have used the dataset full NIH dataset, which contains 112,000 images, around 30,800 patients. And I also use a subset dataset which has around 8,000 images. So here I have captured the distribution levels between the datasets. So this one is for the training dataset, this one is for the validation dataset, and this one is for test dataset for the full NIH datasets. And overall, the levels are distributed equally between these three datasets to help train the dataset in a more uh, uh, proper manner. So here is the subset dataset which I have used, and I have captured the level distribution for the training, validation, the test datasets. So the approach. So basically, I have utilized the approach of transfer learning to build the model. So I have used the model as the PyTorch DenseNet 121 model, and I freeze the base model parameters and only trained on the customized layers which has been updated. Uh, the basic approach is to utilize the image classification knowledge of the DenseNet and add customized layers so that it can adapt to the just extra dataset. So the idea is to extract the low-level features which are common across the images, and low-level patterns and those attributes of the images which are common between the different datasets. So the idea is to utilize those the pre-trained network for those detection analysis, and then update the classification layer to train the NIH datasets. So these are so we can use a network trained on unrelated categories in a massive dataset and apply to our own problem because these are universal low-level features which are common between the images. And the goal is to improve the training time significantly by utilizing the pre-trained model on a large dataset and only training the classification layer parameters so that we can adapt it quickly. Going to the next slide. So I've defined this approach in a diagram here. So the steps are as follows: load a pre-trained CNN model, train on a large dataset, freeze the network parameters for the lower convolutional layers, add custom classifiers with several layers of trainable parameters, train classification layers, training datasets available for the tasks, and fine-tune the hyperparameters and unfreeze more layers as needed. So here is the diagram of the 121 layer dense net architecture provided by Partout. Classification layer in the base model has been updated using the following pseudocode. So I have used the pre-trained network architecture 121 layer, and then in the for loop I'm trying to freeze the uh, parameters for the lower layers, and I have identified the number of parameters in the classification layers. Then I have added two fully connected layers with dropout function as well as uh, prelude for the first activation function for the first layer and sigmoid for the second. Going to the next slide, pre-processing and the training. So in the image pre-processing, basically I'm trying to pre-process the image so that I could use the PyTorch data loader file utility, which requires the image to be transformed in a particular fashion, and the images has to have a be normalized within the mean and the standard deviation as outlined here. I have also used the random resize crop to scale the image to 256, and then I have added color jitter and random horizontal flip. So this is done to create image data in a form which can be processed using the dense data architecture. I have used random horizontal flip for the training dataset to train with different image variants of the image in each epoch so that the model fits the test data better and it doesn't overfit the training images. Training modules loads an existing model if the CKPT file exists and trains the existing model up to max epoch. During each epoch, the algorithm evaluates the model with the validation dataset to calculate the validation loss. If the validation loss decreases in each successive iteration, the updated model is saved. Otherwise, the training continues with the next iteration up to maximum of n epochs without seeing a drop in the validation loss. So the idea is to stop early if the validation accuracy is not improving, and in each successive iteration, if it's not improving up to any port stops. Any port stops. So I've tried to capture the results for the full data set here. So this has been trained only using a single approach because of the large training time. The algorithm was allowed to execute a single approach to the complete data set. Training performed on a single CPU with no NVIDIA graphic package. Training average ROC was observed to be 2.33. Validation accuracy was observed to be 66.8. Training time was observed to be 10, almost 11 hours, and average test accuracy was found to be 0.7. So I've captured the accuracy between the different levels. So almost all levels are hitting zero point 0.7 accuracy, exception of few. So here are the results on the smaller data set. So this data set was allowed to fully execute the algorithm. So we found that it ran for 3 approaches, and we used the early stopping based on 2 approaches. Training performed on a single CPU. Training average was obtained to be 62.5. Validation accuracy was obtained to be 63.8. And training time was observed to be 9,800 seconds with an average of 3,200 per epoch. The average test accuracy was obtained around 0.5. So going to the conclusion section. So basically I've tried to use the pre-trained dense-net architecture, and I have modified the classification layer to adapt to the chestnut chest X-ray dataset. The performance on a smaller dataset is not found to be reasonable because the dataset is very small, and uh, the number of images available are not that many to train the model more appropriately. So upon training the trained model for the single approach full dataset, the average accuracy was found to be more of around 70%. So the performance of the network could be further improved for running the current model using the full dataset up to 10 approaches, and using the early stopping criteria up to 5 approaches. So practically this will take a lot of time because a single approach iteration for a complete analysis dataset takes around 10 hours on a normal CPU which doesn't have a graphic package. So due to the limitation of time and resources, I couldn't train for these many approaches, and my research was limited to single approach full data set. Thank you.